Okay, so today there's going to be a lot of calculation, and I will move fast. If you need to, use your pause button. You may want to just listen through one time and see if how much you can pick up without just going through every little thing. Just get the overall pattern of where we're going. Okay, so the first thing we're going to do today is just compute some descriptive statistics for a single quantitative variable: the sample mean, the sample median, the sample variance, and the sample standard deviation. Okay, so we'll start with a data set. Just consists of these 6 values, 3, 5, 2, 9, 7, and 9. And then to compute the mean, I just have the values repeated back over here, add them up, divide by the sample size. So x bar, that's the sample mean, is equal to the sum of the x sub I, where this capital sigma just means add them up, divided by n, which is the sample size. So the sum is 36. Sample size is 6. There are 1, 2, 3, 4, 5, 6 values. To compute the median, you need to put the numbers in order, which I've done here: 2, 3, 5, 7, 9, and 10. And you want to get the number in the middle. If there were an odd number of numbers, you could just pick the number directly in the middle. Since there's an even number of numbers, you'll find the 2 numbers in the middle. In this case, 5 and 7. Just split the difference. You'll have a median of 6. To compute the sample variance, we'll first take the deviations, that is, subtract the mean, the sample mean 6, from each value of x. So for the first value, 3 minus 6 is minus 3, 5 minus 6 is minus 1, and so on. The sum of those will always be 0. The sum of, I will call these the deviations of x. Deviation just means the deviation of each value of x from the mean. The sum of those deviations will always equal 0. And then we'll move to the next column here where we square each of those deviations. So minus 3 squared is 9, minus 1 squared is 1, and so on. And then we'll add all of those up. So these are the square deviations. And when we get down to the bottom here, we'll call that the sum of squares total, SST, or more frequently just the sum of squared deviations. The SST will come in a little later in the course, or more heavily in the course, when we get to analysis of variance. So anyway, we added those up to 52 and divided by n minus 1. That's the variance. So S squared, that's the sample variance, is equal to the sum of the squared deviations, that's the 52, n minus 1, that's 6 minus 1 is 5. Okay, the sample standard deviation, quite similar. So standard deviation is just the square root of the variance. So follow the same steps. We've got the sum of the square deviations is 52 divided by n minus 1. Then take the square root. So my formula now is S is equal to the square root of the sum of the square deviations divided by n minus 1. That comes out to be 3.22. I think I covered standard deviation a little last week, but just to remind you, standard deviation is just a measure of spread. Think of the weight of cats, house cats, and the weight of house dogs, or at least dogs that people keep as pets. Not everybody keeps a Labrador in the house like I do. But anyway, the pets that people have, the weight of dogs is much more spread out than the weight of cats. Therefore, the weight of dogs will have a higher standard deviation. Okay, so now we're going to move on to some more summarizing data for quantitative variable, but just get a little bit behind those calculations for means and standard deviations and so on. We're going to here construct some frequency distributions, and then we're going to graph those frequency distributions, or at least we're going to graph some of them. So here's just some data on test scores for 50 students. We want to try and get some meaning out of that. So the first thing I'm going to do is create a frequency distribution table. And there are some formal rules for determining the number of classes in a frequency distribution, but I think the guidelines I have here will do fine. Use 5 to 15 classes and use cutoffs that are easy to understand. So just in a presentation standpoint, like if you were doing percentage grades, like on an exam, you would want to go 90 to 100, 80 to 90, and so on. We'll get a little more exact than that in a minute. So we'll need to get the class limits. Greater than or equal to 90 but less than 100, greater than 100 but less than 110, and so on. Be careful in this definition. What I want to do is have something precise. So, for example, since I can see it here, let's say I had a value of 178.7. In my case, 178.7 clearly goes in the class greater than or equal to 170 but less than 180. But if we had defined this class as 170 to 179 and then 180 to 189, where do you put the 179.7? Anyway, I'd like for you to define them like I do. There's just no question there where values need to go. So now I'm just going to tally up the number in each class. You'll have to take my word for it. There are, well, I guess you can count them up. You don't have to take my word for it. There were two numbers in the class greater than or equal to 90 but less than 100, then 5 in the next class, then 10, and so on. So I just tallied those up, and now I'm just counting those. And so I have, this is a frequency or absolute frequency distribution, which just has the classes greater than or equal to 90 but less than 100, and so on, and the frequency in each class, the 2, 5, 10, 14, 10, and so on. I'll call it an absolute frequency distribution or just a frequency distribution. There are going to be some other frequency distributions that you'll always want to have the modifier with, but if you just say frequency distribution, this is the one we're talking about. Okay, a relative frequency distribution, we're just getting the proportion of values that are in each class. So if there are 50 total values, which there are, in the first greater than or equal to 90 but less than 100, we'll just take 2 divided by 50 and get 0.04, and so on down the line, 5 divided by 50, 10 divided by 50, and so on. And these are just the proportion of values that lie in each class. Later, when we'll talk about probability distributions, a relative frequency distribution and a probability distribution are basically the same thing. As I've noted here, one advantage of a relative frequency distribution is you can easily compare two relative frequency distributions. For example, if you had two data sets, one with 1,000 values and one with 100, if you just did the absolute frequency distributions, it's difficult to compare them because the 1,000 is going to have more in every class just because the sample size is larger. But when you get to the relative frequency distribution, you're using an out of one scale, and so it makes it easier to compare the two distributions. Okay, cumulative frequency distribution just reports the number of values that lie below each class limit. So the first class here, less than 90, so I just took the original greater than or equal to 90 and just went below that class. The cumulative frequency was 0. The next one is less than 100. There were two values there. For less than 110, just take those two, add the 5 that were in the class greater than or equal to 100 but less than 110, and you'll have 7. And then go the same kind of way through the list here. 7 plus 10 is 17. 17 plus 14 is 31, and so on. When you get down to the bottom, that last number should be the size of your sample, or in this case, 50. You can also do a cumulative relative frequency distribution. The relative frequency in less than 90 was 0. Then 0.4 in the first one, plus 0.1 in the next one is 0.14, plus 0.20 was 0.34. So now we have the cumulative frequencies, and that should end up with, in the last class, the less than 190, you would have 1. In other words, include all the values in the data set. So now you can look at this and can answer some questions just by reading off here. What proportion of values are less than 140? That would be 0.82. What proportion of values are in the class 150 but less than 160? That's 0.06. What proportion less than 160? That's the 0.96. How many in the class 120 but less than 130? The frequency is 31. Then you could get the cumulative frequency the frequency is 14. The cumulative frequency is 31. Got ahead of myself a little bit there. The relative frequency is 0.28. And the cumulative frequency, that means from starting at the beginning on up to 130. In other words, less than 130, you would have 62% or 0.62 of the data. Histogram is just a bar chart for a quantitative variable. The one difference between a bar chart for a qualitative variable and a quantitative variable is for a quantitative variable, the x-axis has a quantitative meaning. So you can see that 80, 90, 100, 110 on the x-axis for the scores, and then we're just counting the number in each category. When we had a qualitative variable, or if we had a qualitative variable, the bar chart would have gaps on it, and you would just say Group A, Group B, and Group C. With the histogram, there will be no gaps, because for that first one, we're not greater than or equal to 90 but less than 100, greater than or equal to 100 but less than 110, and so on. And so just take those counts from the frequency distribution and make a line equal to it. So for example, in the class 120 to 130, we have 14 values. In the class 180 to 190, we have one observation. So interpreting a histogram, first thing we're going to look for is the center of the distribution, which in this case is in the class 120 to 130. Given that this is a roughly symmetrical distribution, we would expect the mean and the median to be in this class as well. Since it's the highest class, we already know it's the modal class. So instead of having a mode of one value, now we have a mode for the whole class. And that class 120 to 130 had 14 values in it, and that was more than any other class. Then we can look to see how spread out the data are. Especially if we had more than one histogram, we could look and see which one was more spread out than some other distribution or distributions. And then we might note here that looks like we have one value that's unusual, which we'll call an outlier. We'll actually talk about outliers and extreme values, and I'll make a distinction about that a little later on in the lecture. Also need to look at the shape of the histogram. In this case, it looks like a bell curve. And that is one shape that will show up over and over again, and you should be familiar with that idea. In fact, the bell curve occurs so frequently that it's often, and in fact usually, called the normal distribution. So here's another important shape, that is skew. This one, skew to the left, drops off to the left, as opposed to this next one, which is also skewed, but it's skewed or dropping off to the right. One of the reasons we're looking at shape is because that's going to affect the sample size that we'll need for valid statistical inference when we get to that part of the course. And so the things we want to look at are the shape, whether or not it's a bell or skewed. We'll also want to look for the presence of outliers and extreme values. Again, more about that in just a few moments here. Okay, creating an ordered array, that just means putting numbers in order. If you just have 5 or 8 or 10 numbers, that's easy enough to do. But if you have quite a few numbers, we'll want to make this a little bit easier. If you have to do it by hand, you want to use a stem and leaf plot to make it easier. If you have a calculator or software, then it's almost effortless. But right now I'm going to use a stem and leaf plot, so let's say you don't have a calculator. You need to know what a stem and leaf plot is anyway. So I start with a stem here. The numbers in the data set range from 90 to 182, so I'm using stems of 9 to 18. That is whatever in the tens place, so 90 would be 9, and then the 18 goes with 180. So here's some values in the data set, 127, 113, and so on. So let's look at the 127. We'll go over to the 12, that's 120, and then add a 7 next to that. That's 127. Then for 113, we'll go to the 110, the 11, put in a 3 next to that stem. I'm going to skip down a little bit to the 128. Now I'm just putting a comma next to the 7, so now I have 127 and 128. Then just keep going until you have them all. So here are my stem and leaves. What I've done now is put in the leaves, put all of those in order. So the 8, 9, 3, 3, 4, 7, 9, so I have them in order in each one. Not that hard to do for a few numbers. One thing you might note about a stem and leaf plot is if you turn your head 90 degrees there, then you have a histogram. One advantage of this over a histogram is that you retain, not only can you look at the shape and the presence of outliers, you retain the actual numbers that were in the data set. And here's just a stem and leaf plot generated with SPSS, one of the statistical packages that you can use for this, generated by using a pull-down menu, Analyze, then select Descriptive Statistics, then Explore. Then you'll get to a dialog page and you need to move your variable over and then basically click OK. In fact, not only will you get a stem and leaf from that, you'll get a box plot. You can give it an option to get a histogram as well, and it'll also compute, just using this one procedure here, the mean, the standard deviation, the variance, the median, and a few other things. Okay, so now we're going to summarize locations in an ordered array. The main thing we're going to use is the 5-number summary and the box plot, which is simply a graph of the 5-number summary. We are going to use box plots a lot to identify outliers and extreme values, check assumptions for inferential tests that we'll get to later, help you determine what sample size you need for valid inference, and to visually compare 2 or more groups. You may remember a few years ago a little bit of a problem with a restaurant that someone sued them because they spilt their coffee in their lap when they were driving. A lot of people got a lot of jokes out of that, like Leno and that kind of thing on the late night shows. But it turns out that the company in question really was heating their coffee to abnormally high temperatures. But anyway, that's neither here nor there on this. We've got 24 cups of coffee and the temperature of each. Well, I can tell you that 204, that's a pretty hot cup of coffee. So I'm going to put them in order. You can tell that I did this with SPSS because it put in the 0.00 after every number. But they're still the same numbers. Now they're in order. So the 5-number summary, you get the numbers in order. The first number is the minimum. The next is the first quartile. That means 25% or 1/4 of the values lie below a particular point. The median we already know, 50% of the data below this point, 50% above. Third quartile or the 75th percentile. And then the maximum value. So let's look at this in this example. The minimum is 165, the maximum is 204. That's easy enough. The median, I'm giving you 4 columns of numbers to make this kind of, I hope, very obvious where things are at. If you look at 176 and 177, you've got half the values on one side, half the values on the other side. So we're just going to split the difference between the 176 and 177 to get the median. So the median in this case will be 176.5. We'll do similar things for Q1 and Q3. So at 172 and 173 have 1/4 below, 3/4 above. So we'll just take that 172 and 173, split the difference to get 172.5. And similarly for the third quartile, we'll come over and get the bottom number in that third column, 182, and the top number in the fourth, 183, and just split the difference and get 182.5. Some would argue, like for the first quartile, instead of just splitting the difference, you ought to only go 25% of the way. You'd get 172.25. But really, any number between 172 and 173 fits the definition of having 25% below and 75% above. So we'll just split the difference as an easy way to do it. And most calculators and most computer programs would do that as well. So there's just a summary of that, the 5-number summary. So the box plot is just a graph of that 5-number summary. So we'll draw a box from Q1 to Q3, from 172.5 to 182.5. Then we'll put a line in the middle of that. That'll be the median. Then we will extend whiskers to the minimum and maximum values. I think that upper value was 204. I can't remember exactly what the lower one was, but must have been around 165. Now I'm going to show you how to use the box plot to identify outliers and extreme values. An outlier will be defined as a value that is more than 1.5 interquartile ranges from the box. Interquartile range is just the difference between Q3 and Q1. We'll get to that in a minute here. But anyway, to get the upper fence or cutoff or outliers, would take the Q3 value and add 1.5 IQRs, and if we were looking on the lower end, we would get the lower end of the box, 172.5, and then go 1.5 IQRs below that, and see if we can identify outliers down on that side. So the inner fence is what we use to identify outliers. Again, those are the ones that are 1.5 IQRs away from the box. So as I said a moment ago, the IQR, or interquartile range, is Q3 minus Q1. In this case, that comes out to be 10. Multiply that by 1.5. We got 15. So now we're going to go 15 units above the box and 15 units below the box to get fences or cutoffs. So Q1 minus 1.5 IQRs, or 172.5 minus 15, 157.5. Since our lowest value is 165 and that's not lower than 157.5, there are no outliers on the lower side. By contrast, on the upper side, we'll get 182.5 plus 15. That's the 1.5 IQRs. Okay, I can see a mistake in my typing here. That should be Q3 plus, or 1.5 times that. Sorry about that. I had the math right, I just forgot to put in the 1.5 there. Anyway, the cutoff is 197.5. We have a value of 204, which is greater than that, so there is an outlier on the upper side. Extreme values will go 3 IQRs above and below the box. These will be outer fences, or just the cutoffs for extreme values. So we've got the IQR again, that's 10. Multiply that by 3, 30. So we're going to go 30 above the box or 30 below the box to identify extreme values. And the lower fence will be Q1 minus 3 IQRs, and so we're subtracting 30 from Q1. Of course, if we didn't have any outliers on that end, we of course can't have extreme values. That would be even further away. Then the upper fence, we add 3 IQRs at 217.5. Therefore, that 204, though it was an outlier, it's not an extreme value because it's not higher than 217. So let's add a fence to the box plot. We'll draw lines to get the upper and lower fences. I think those were, 157.5 and 197.5. I'm going to add asterisks for points that extend beyond the outer fences, which are not applicable in this problem because we don't have any extreme values. An asterisk goes for an extreme value, at least in the package we're going to use, SPSS, and that really is the most frequent symbols, but I have seen other programs that do it differently. So now we're going to add a small circle for any point that extends beyond the inner fences. In this case, they're just one value, and you can see I've got a little circle out there for it. Then I'm going to shorten the whisker, and I'm going to shorten it down to the last value that is not an outlier. That must have been around 192 or so. Well, now it looks like it was 197. I'll have to go back and check that. Anyway, that value where the whisker goes to now is the last value that's not an outlier and not an extreme value. Well, anyway, what do you do with outliers and extreme values if you find them? First of all, let's ask ourselves if there was a data entry error. We could also ask ourselves, did someone purposely microwave the copy to a boiling point? Maybe a disgruntled employee. Or are coffee machines designed as a matter of policy to make very hot coffee? So assuming it wasn't just a data entry error, you want to study outliers and extreme values. Look, what's the cause of it? Example I like to give is if this were performance, the most interesting person in the whole company might be that one outlier. What we'd like to do is study that person and see if we can replicate that high level of performance for everyone else. So here's just a box plot that I created with SPSS. No outliers, and the median's about in the center, and neither whisker is a whole lot different than the other one. So it looks like we have a symmetric distribution, and this certainly is at least consistent with, or at least not inconsistent with, the idea that we might have a bell-shaped distribution. So now here's one that has an extreme value. You can see the asterisk up there. Now that number 1 that's right, that just means that it's the first point in the whole data set. If it had said 14, you would go down to the 14th element in the data set, and that would be the element that has the extreme value. Looks to me like we might have, except for that one value, something that's close to a bell curve, but we do have one highly unusual value. This might be the pay in a company where the one person at the top is the CEO or president of the company, or the owner. So here's one with 2 outliers, and you can see with the 15 and 16 that those are the 15th and 16th values in the data set. Also looks like kind of skewed there. You can see one of the whiskers is quite a bit longer than the other one. And that's borne out by the histogram as well. Okay, let me go to a couple of things here that are matching just to give you some sense of the kind of things that I think this will help you understand some things a little bit better. And so we'll just go to this first one here. I'll put links to these on Blackboard. Quite frankly, I ask a lot of multiple choice questions on the test based on maybe a lot of them, but okay, I paused there, and I guess the link didn't work, but I went ahead and found it in another way. I'll put the correct link on thing. What you can see is that I've got 4 histograms followed by 4 sets of means and standard deviations. So what I'm going to do is match these up, and let's see, on the far right hand side you see I have a mean of 5.7. The other means are 12.4, 13.7, and 7.2. Well, this looks like the only one that can have a mean of 5.7, and you can see I got that correct. And then another thing I'm going to look at here is I have one that has a standard deviation of 5.7 and a mean of 7.2. Well, this one on the far right looks to be the most spread out of the data set. That's the easy way to find that. And then the other two I have, this one will be a little tougher. So means are 12.4 and 13.7, and the standard deviations aren't that different. But it looks to me like the one over here has a little lower mean and just slightly more of a, and then I can move over here. Okay. Well, anyway, you ought to go on to this website, and you can do as many of these as you want to. Maybe I'll just do one more here. Small standard deviation around 8. Another one with a relatively small standard deviation. Here we go. And then on these two, it's pretty easy to see that this one's going to be the mean of 8, and this is the mean with 3. Okay, I'm going to pause again and find the next. Okay, this one asks you to match histograms and box plots. And so let's see here. You can see a box plot here that's really spread out from the top to the bottom. You might think that first one would have outliers, but the whole thing is not really clear center or anything. This looks like it might have a couple of outliers. It's okay. The other two look, I think I'll get here, the mean's closer there. The mean's a little bit higher. And I want to talk about computing covariance correlation coefficient, that's R, and then the slope and the y-intercept for a line. As you're going through, really try to understand the calculations, not just memorizing the formulas, and I think you'll have a pretty good understanding, especially of covariance and correlation. I have to admit the slope and the y-intercept, the formulas, I'm not sure they help as much as they do for the covariance and the correlation. But anyway, here we go. We've got observations for 2 variables, x and y. I didn't do it here because I just want to focus on the calculations. But really what I should have done in the first case was draw a scatter plot to just get a graphical representation of this. Anyway, compute the 2 sample means. Got 6 and 7. Then compute the deviations. I'm subtracting, in the first one, the x is subtracting 6 for each value. And then for the second one, for the deviations of the y, subtracting 7 from each value, since that was the mean for the y's. And of course, the sum of the deviations for both of those is going to be 0. I'm going to get the obtain and sum the cross products. That's the product of the x deviations and the y deviations. I'm going to leave some space there because I'm actually going to have to compute the standard deviation. I usually do it this way because when I start having to skip across columns and stuff, I'll lose my place. A little bit easier here. So in the first one, 0 times 2 is 0. 2 times minus 4 is minus 8. Minus 3 times 1 is minus 3, and so on. And then I'm going to sum those. That minus 23 is the sum of the cross products. So the sample covariance, the COV xy, is equal to the sum of those cross products divided by n minus 1. So that minus 23 divided by 4, there were 5 values there. It's minus 5.75. So one way to think about this, in fact, I think the best way to think of this, and let me go back a slide here. When you look at this covariance, at the first one, what that's saying is that when x is right at its mean, y goes 2 units below its mean. When x is 2 units above its mean, y goes 4 below its mean. When x is 3 units below its mean, y is 1 unit above its mean. So we're getting a sense of how they move together. In fact, all these negative numbers over here would indicate that we're going to have a negative correlation and a negative slope. So let me move back over here. So now I'm going to calculate the two standard deviations just as we have done standard deviation before. So I've squared the x deviations and summed them to get 26. Squared the y deviations and summed them to get 34. And then just calculate the standard deviations for x and y just like we had done earlier. Standard deviation for the x's, the sum of the squared deviations divided by n minus 1, got that to be 2.55. And the standard deviation for the y's is the sum of the squared deviations for y divided by n minus 1. Take the square root of the whole thing, got 2.92. And then the correlation is simply that covariance, the minus 5.75, divided by the product of the two standard deviations. So minus 0.77 would be the correlation coefficient in this problem. And that's how to compute R, the sample correlation. Maybe remember from last week, that's our estimate of rho, the population correlation coefficient. Okay, the formulas for the slope and the y-intercept. For the slope, take that same covariance of x and y and divide it by the variance of the x's. And then the y-intercept A is just going to be y bar minus b times x bar. By the way, I know that the symbols here are a little bit different than you had in algebra. I guess that's the simple answer. Now, the way we do it, reason we do it this way is, this is simple correlation or simple regression when we get this equation for the line here. But what we're going to have is A, the y-intercept. Later on, it'll be A plus b1 x1. So you have a slope and and 1x. Then you have plus b2 x2 plus b3 x3 and so on. And so we just, starting at the left, call the intercept A, and then after that we'll have b1, b2, b3. In other words, we won't just predict x with one variable, with many variables. And when you get two slopes, then you're in a plane, three-dimensional space. After that, I'm not sure what it looks like, but I know what the formulas look like. I just don't have the geometry in my head. I suspect you don't either. So the slope then is, I took the standard deviation of the x is 2.55, squared it. So the covariance divided by that, minus 0.88. So that means for every unit x, looks like y, change in x, y goes down by almost 1, by minus 0.88. I don't know why I did that. But anyway, the intercept is 12.28. That's just the point where the line crosses the y-axis. So now we're just going to start with just a graph and get the y-intercept and the slope from that visually. I guess with a little bit of drawing along the way here. So here's two quantitative variables, x and y. It just means each row of this is one element, one person or one product or whatever. Now I'm going to draw a scatter plot of that. That's just plotting the x's and the y's. You know, in algebra, every point would have been exactly on the line, but here they are not. So I'm going to estimate the intercept and the slope. So the intercept's about 40. You can see if we drew a line here, I should have drawn a line on this, but the line would go something like this. The intercept's going to be about 40. And then, I thought I had a line on this. Let me see here. Give that another try here. Depth is around slope. First, going to just find 2 points. I'm going to choose 10 and 20 because, I like to have 10 in the numerator. Remember, the slope is going to be the rise over the run. The run is 10. And then the rise is about 40. So now my rise is just from here to here, and you can see those over on the y-axis. So that goes from about 125 to 85, and that's about 40. So the slope would then be the rise over the run, or about 40 out of 10. 40 over 10, or 4, for the slope. Maybe it doesn't look like it's 4 in this case, and that's just because the axes are on different scales. Now I have an equation for the line. The y-hat just means that it's predicted y is equal to a plus bx. Remember, a is the intercept, b is the slope. So a is 40 and the slope is 4. Go ahead and say right here, we'll have more to say about this again a little bit later. To predict a value of y, if I plugged in, let's say 35, I can just plug 35 into that equation. 35 times 4 would be 140. Plus 40 is 180, so you just go and look on the x-axis here for 35, and then go up, and you ought to have about 180 on that line. Be a little careful about this because our x's went from about 0 to maybe 45 or so. If I asked you to make a prediction for x is equal to 100, you shouldn't do it because our line is only good for the domain of x values that we have. It looks like close to 0 up to around 45 or 50. What happens to the line after we get to about 50? It could